For scenario number 1, where the x initial is 30 centimeters and the initial momentum is 0, the A coefficient is equal to the initial x position. The beta is equal to the dampening coefficient divided by 2 all over the mass of the block. The omega is equal to the square root of the spring constant times 1.035, all divided by the mass of the block. The phi value remains 0.
So when we run this simulation, we see that the computational model and the analytical model are on top of each other. If we were to change the dampening coefficient, these amplitudes would get smaller faster.
For scenario number 2, the A coefficient is equal to the x initial plus the initial momentum divided by 20 over 9. The beta is equal to the dampening coefficient divided by the mass of the block. The omega is equal to the square root of the spring coefficient times 1.035, all divided by the mass of the block. The phi value is 29.8.
And this is for the scenario where the x initial is 0 and its momentum is at 100 kilograms centimeters per second. And when we run the simulation, we have the overlapping graphs of both models. This model also works if we were to change the momentum to a different value. And we can also see how the dampening coefficient affects the amplitude. The distance decreases much faster.